Yes, now we can start. Thank you. So, good morning, everyone. I'm Luís Correia. I'm with IST at the University of Lisbon. And it's a pleasure to be here this morning to introduce the other two keynotes of this conference, which are colleagues that are well known for most of us, I would say. And we start with Carmen Mas-Machuca. I think I pronounced the name more or less correctly. Carmen, gracias. So Carmen is a full professor with the chair of communication networks at the University of Bundeswehr Munich. So she has a very long CV, which I'm sure you can read. And if I was reading her CV here, I think I would spend half of the time, so I think it's better that we listen to Carmen. So Carmen, please, thank you very much for coming. It's really a pleasure to have you here. Thank you.
So thank you, Luis, for the introduction. Okay, so good morning, and thank you for coming, despite being 9 a.m. in the morning. So my talk is on planning and operating secure and resilient networks. Mainly the motivation, let me see if it works. So it has been already mentioned several times during the conference about the fast evolution that mobile networks had in terms of capacity, services, delay requirements, availability requirements, and so on. But we don't have to forget that all these requirements do not affect the mobile network, but also fixed networks. Both mobile and fixed networks have to coexist, and they both have to cope with this increase of requirements. So optical communications, which are the most important technology for fixed communications, backbone networks mostly, and also the technology that is interconnecting base stations, data centers, and so on, has also increased a lot, has evolved a lot in the last years. So you have much higher capacity. Now we are going to have terabits per second per fiber. You also have security, QKD, next generation and very high speed PONs technology that are offering 100G PON, 200G PON capacities to the last segment. We have coherent technology that is able to increase significantly the reach, and so on. So you have a lot of evolution also in this technology that is improving the spectrum utilization using the same fibers that they have been being installed for many years, and just by upgrading the technology at end sites, you are also increasing capacity and to go with the requirements, so also very low delays and so on. Just taking, I am not so much on the mobile, but just I wanted to look into the how 5G has evolved, and I look into this 5G European Observatory, and I compared the data that we had in April 23 and the one that we have in June 25. For some of the countries, I did not gather the data for all of them. But you can see that there has been a significantly increase of the number of base stations that are using 5G. This means that, okay, I mean, 5G, you are increasing coverage, you are increasing the services of all these 5G users, but also all these new base stations have to be connected. How they are going to be connected? Because usually they are new sites. Few generations ago, there were all these microwave links in order to interconnect, aggregate the data towards the fixed network. But now, because of this increase of capacity, the communications base station had to be interconnected with optical fiber. That is the one that is able to go with the high data rate that is required. So there is an issue on how to interconnect these base stations, which topology they are going to use, how they are going to be interconnected, because this is also going to be a very critical aspect in the resilience of this mobile backhaul. So regarding the reliability requirements evolution, I tried to gather also some data, and we have seen that, okay, many years ago, back in the 80s, we were just having phone services, and we were accepting some service interruption, and well, there were some reparation times. Then came the famous 5 nines availability for the telephone, for the PSTN network. But then more services, internet, computers came into the game. We have this interconnection of new devices. And there we had not only, so usually we had restoration by finding a new path to keep the connectivity. Later on, we start with the service level agreements, these SLAs, where the customers and the provider are able to agree on which is the maximum downtime, the MIDT, allowed per year. And this is a very critical parameter for operators. Operators have to reserve enough resources in their networks so that they can guarantee not to exceed this maximum downtime per year. In case they exceed, usually they will have to start paying penalties because it will affect the customer's business somehow. And these penalties are usually exponential. It's not linear, it's exponential, because the longer the interruption time is, the higher the losses of this potential customer business. And that's why it's very critical for the operator to know which is the service level agreement that they sign, which resources they reserve, so that in case of a failure or an attack and so on, they can cope with all those requirements. Then, of course, mobile technology came. They are increasing the number of nines. At some homes, you have 4 nines. Then clouds and hyperscalers came to the resilience as well, and they know that failures can occur, but they just have to design a way that the network and the operation of their services, cloud services, can still run even despite having failures. And of course, 5G came with this up to 7 nines availability, so around 7 nines. So we have an increase of reliability requirements. And the last one is this. In ITUT, we have this report where they mention the need of having security and availability on the services that is very critical, but without specifying any numbers for the fixed network. So we know that failures, disasters, attacks occur in networks, right? We are not aware about how many they occur, because usually the operators are not very happy to share this data. So we only learn them from reports or from the news whenever it's a really high impact. So operators will know, but we don't know. But we have gathered some, all the data because we couldn't get a little better. But at the EU, system failures accounted for 93% of the user hour losses in 22. Natural disasters have increased by a factor of 3 with respect to 2019, so in 3 years with a factor of 3. So every time we have more natural disasters, interruption, failures in our networks. Also, a key issue is these undersea cables. All these submarine cables are now becoming very critical infrastructure, because they are interconnecting all these continents or surrounding continents, and most of the traffic is going through these submarine cables, so optical cables. So this also is a very critical infrastructure. So if we look into some of the news that we could get through the news and through the press, we can see that interruption of optical cables can interrupt not only communications, but also train services. We can also see the dependency of the power failure that we had here in Spain with a communication network that drop the core traffic to 17% only. You also have these natural disasters in the case of Sydney in 2019 that interrupted all the mobile network, not because they were burning per se, but it's because they didn't have the power that was powering all this telecom equipment. And this triggered now that in Australia they are asking operators to publish the failures of those critical infrastructures so that they are aware and they are able to coordinate, which I think is really a good metric. We also have our Baltic Sea issue about all these cables that are interconnecting the north part of Europe, and they are having these cable failures with all these unknown ships. Also in Argentina, they had the optical fiber cut that interrupt the services of mobile and fixed users. So only the ones that are gathered in the news are coming into our hands. But what is the problem for operators? So if we take the role of operators or hyperscalers and so on, So you have these two types of technology. You have the 6G that they are asking for low latency, high reliability, massive connectivity, high rate, coverage, and so on. And we have the same in the optical domain. So whenever you talk about the optical backbone network in a national, international level, you also have high reliability, robustness, capacity, security, low energy consumption, and so on. But what you have to think is that now, as users, we want to get information of any service about any time, anywhere, from any device. And this is what the operators are trying to get. And for that, both worlds, mobile and optical, have to work together so that they are able to guarantee these requirements from us the users, and also of all these AI, ML between data centers and so on. So for operators, you have that they have this increase of service requirements. The services, every time they are becoming more restrictive in terms of requirements. You have a much higher of demands. We have more users. We have more devices that are connected to the network. And also operators, they have to keep upgraded all the service portfolio. And for that, operators need to upgrade their networks constantly. Yeah. But also, on the other hand, you have now more operators. I mean, years ago, we only had one operator per country. Now you have several operators for both mobile and fixed network. This means that it's easier for us to change from one operator to the other. And also, you have the role of regulators, which are also keeping the fair play in this telecom market. So you have all these players, and you cannot put the price for the service as high as you want in order to keep having revenues. You have also the competition, and you also have the regulators. So you have a control set of revenues. So at the end, you have a compromise there of how much investments do I have to put in my network to keep upgrade the capacity, the reliability, the delay, to cope with all these requirements, and at the same time, keep all the competition and be competitive in this market. So regarding the network evolution, just an overview. So we have many technologies, optical, wireless, satellite, mobile, and they all have the advantages and some limitations, and that's why all these technologies will coexist in the telecom arena. The services, they are keeping increasing, and they are very different, like autonomous driving, virtual reality, industry sensing, e-health, smart city, and so on, smart grid. And all those services have very different requirements in terms of which is the capacity they need, which is the reliability, which is the delay, latency, security, sovereignty, and so on. So, and you also have many different players. So before we had the one single operator in a country, and now you have the physical infrastructure providers, the network providers, the service providers, you have the hyperscalers, the virtual network operators, and so on. So the networks are changing significantly. So my talk, I am going to split it in two parts. First, I'm going to talk about the physical infrastructure planning, taking into account how to make it robust, sovereign, and secure. And then the last part of my talk, it will be more on the network operation, so how to set up a reliable and a secure connection, so service. So if we start with the physical infrastructure, how can we design a robust network, right? And one of the definitions of network robustness is the availability of this network to maintain the functionality. It could be connectivity. It doesn't have to be connectivity, but the functionality when components fail or are attacked. Yeah? So if we look into, I just put as an example, backbone with the main cities. And if you think that this is a greenfield scenario and you want the connectivity of this network and you have not so much money, you will start with a very basic tree that guarantees the connection between any pair of nodes. A tree, as we know, so you have it's little investment. You minimize the number of links that you will need in this network, but at least you can guarantee that you have a connectivity, right? You can exchange information, but you know that if you have a failure, you will have a disconnected graph. The next step will be to have at least a bi-connected graph, which guarantees that between every pair of nodes, you have two disjoint paths. This means that you are able to keep the connectivity even if you have one single failure in your graph. But this may not be enough, so if you keep investing on your network, you can have a partially meshed network, and in this way, you are not able to find only 2 disjoint paths, but for even you are able to cope more failures, simultaneous failures, you are able still to find the connectivity between 2 network nodes. Of course, if you are super rich, you could have even a much more meshed network. This comes with serious investments. And this is a bit the trade-off that operators have to have, right? How much investment I have in my infrastructure so that my network is more robust. So in order to evaluate robust, so far I am talking about failures. Failures can be assumed to be random because you don't know where they can happen. There are some, of course, they are characterized by some failure rates, and you have some distributions and so on, so that you can estimate where the failures could be. But if you are thinking about an attack, and you are thinking about the bad guy that knows about your network infrastructure, he may have a particular strategy to decide which node in your network may attack. And for that, so the idea is how to measure robustness, exactly. So is it connectivity or is the capacity, and against what? Yeah? So I talk about the failure, the random failures, or we can go to the centrality metrics. Centrality metrics are, as the name says, so metrics that define how central a node or a link is in your network. So you can have node centrality, to how many nodes this node is connected, or you can have closeness centrality, how close is one node to any other node in the network. You can define betweenness centrality, how often this node is part of a shortest path between any 2 pair of nodes. You can have also eigenvector centrality, that is how good connected my connections are. Yeah? So it's a bit like social media. It's better to have 2 influencer friends than to have 5 non-influencer friends, right? So these centrality metrics could be used by the bad guy in order to decide which node of the network will be attacked or fail, and this is expected to have a high impact on the performance of your network. You can also evaluate what happens when those attacks or those failures occur by evaluating some structural metrics. So you have the relative size of the largest component, so how many nodes are interconnected, or you have the connectivity, so how many connections a pair of nodes can be connected, or you have the min-cut sets. Min-cut sets is the set of components whose failure will cause the failure of the network, or the disconnection of the failure of the network. So you have different structural metrics there, and at the end, you have to evaluate how robust your network is. And for that, we propose always the robustness surface, which is this diagram where you can test different failure scenarios. So in the x-axis, you have different failure scenarios. And in the y-axis, you have how many nodes have failed, if you are considering node failures. So you will say, OK, randomly, I will choose one node that fails. Randomly, I will select another node that fails, and so on. And then I will evaluate one metric. In this case, it's the connectivity. And having this heat map, you can see how fast, for the different random failure sets, how my connectivity is dropping. What can I do with this robustness surface? So for example, I could compare how different metrics are degrading with the same set of failure scenarios and see, for example, that this relative size of the connected set is dropping slower than the connectivity. You can also see, and this is important to keep in mind, that when you compare how all those metrics change with the different failures, they are not always decreasing. And this is something that you have to take into account whenever you are calculating this robustness surface, because you have to take into account if this parameter is always a non-decreasing function, or you also have some increases, so depending on the metrics. From this robustness surface, you can also compare this line, robustness line, where you have now in the x-axis the number of failures, and the y-axis the metric. So you can see the degradation, for example, of the connectivity for random failures. And this is easier to compare whenever you have targeted failures. So if you assume that the bad guy, is considering the between centrality as the approach to detect which node is going to fail, you can compare the degradation of the connectivity in your network. And you can see that if you have 15% of the failures of the nodes has failed, the random is affecting less the connectivity than the targeted alarms, failures, right? So it's something important that you have to take into account, right? Operators have to go with any type of failures and any type of attacks. You have to compare many different metrics, and all these surfaces will help you to do this comparison. What it was interesting to see is that if you have a low percentage of failures, in this case 5%, you don't see an impact whether it is random or targeted. And in fact, when you compare all these metrics, even the random is even performing a bit better than the targeted ones. And we saw why this happens. And can we propose a metric that in this is really looking into the worst case scenario? So like helping to the bad guy to do a worse performance, or helping the operator to be better prepared against those failures, right? And we propose this K-score, which is taking into account these mean cut sets I told you before, how many minimum cut sets your graph has, how big these cut sets are, how often a component is in those mean cut sets, and like that we can identify which is the most critical component in your network that will affect the most. And we saw that indeed taking into account this metric is decreasing, affecting much more the connectivity in your graph. Okay, so how to define a more robust network? We have seen that, okay, increasing the connectivity will increase the robustness because you have more ways to reach your destination, right? But it's not only about connectivity. We have to take into account that we also need capacity. How much spare capacity operators have, this is also an issue. Spare capacity is a capacity that it is there, and nobody pays for that because nobody's using it. It will be just there just in case there is a failure or an attack. So it's not helping the business. And the target for operators is to minimize this spare capacity while coping with all the availability requirement by the customers. We also have to be aware about how networks work nowadays. So as you know, now we are going to software-defined networks, so we are having the same hardware, and we are just upgrading the software there, which most of it is open source. And what happened is that this open source has more failures because there are more developers, there are more bugs, and so on. But the impact of those failures is less than the hardware failures. So you always have the compromise of how many of those failures have and which is the impact of those failures. So it's something that we have to take into account about this compromise. Also, what it is very important is to reduce the dependability. And what I mean by dependability, so is, as you know now, communications networks need power for their components, right? It's not only about power, but also about air conditioning and so on. So communications network depends and has this dependency on power grid networks. But also, power grid networks has a dependency on communication networks. Now they have these power grids that they have a bidirectional energy distribution. They need to control and to manage better the consumption of the power and the generation of the power. And they rely on communication networks. So these two critical infrastructures depend on each other. And what we saw, and was this first analysis in access networks, is that the consideration of power failures into the communication availability has a high impact. So in this Sustained Advanced project, and you have a booth also here in EuCNC, we are looking into this reduction of dependencies. How can we model, and how can we reduce the dependency on these two critical infrastructures? And then another important term is sovereignty. Yeah? So how we do define sovereignty in our case is the availability of the network to maintain the functionality and the connectivity when a manufacturer component fails or are unavailable because of loss or because of, yeah. So just to give you some example, there was this famous CrowdStrike bug in the operating system that made all the Canadian ministries' PCs were blocked and they were not working. It was because of the same problem of this security issue. Also, you know that in some countries are going to ban some of the manufacturers, and this will prevent the use of those components in the networks. We also have the recent news in January of EU from suppliers of high-risk countries. You also have the case of the Galaxy Note 7, that they had this battery problem and they had to be removed from the market. So you never know when there was going to be a manufacturing problem or a new law that is going to prevent the use of a particular manufacturer. And for that, we are trying to compare what the availability from the reliability perspective and the one of sovereignty. So they are two different terms. So whenever we talk about availability, usually we have to select which component we want in order to have a higher availability of our service. So usually you will say, okay, which is the availability of a particular component, and I will have components that have more nines availability in order to guarantee that my connection is going to have a high availability, right? So in those cases, when you have failures, they are independent. Whereas in the sovereignty problems, you will have to select which manufacturer I'm going to have. Of course, they are where I am going to place those components and how many manufacturers do I need in my network, so that if one manufacturer fails, and this will imply that all those components will be banned or will fail at the same time, my network needs to still be operating and running and offering the expected services. So it's a bit the difference, right? So whenever we were thinking about this sovereignty, we saw that there is no real metric on how to evaluate the sovereignty of a network. So we have proposed one, but we want to see what is required is that really for this sovereignty metric, there has to be an agreement not only from operators, but also from manufacturers, regulators, and governments. They have to work together to see really what can be done against that. If there are going to be some requirements, some specifications, some rules, some laws, and so on. It's also important to say at which level. So it's not enough to say, okay, Huawei is going to be banned, for example, but are we talking about routers? Are we going to talk about CPUs? Are we going to talk about which type, at which level, component, subcomponent level, right? And then we thought from the operator point of view, which is the network planning problem? So we have defined this manufacturer placement problem that we want to identify how many manufacturers should be available in the market, because it's not that we have a lot of choice, where should be placed, and whether they are interoperable with each other. They are standardizations, but as you know, standardizations, they are complying with the standardizations, but some manufacturers are adding some extra features that, of course, they are not available whenever you put it with other components that are from another vendor. So the idea is to guarantee this interoperability to be able for the operator to interconnect all those different equipment together in the same network. So our planning problem was, given the network, given the expected traffic, and how many manufacturers are available in the market, so find which is the best number of manufacturers and where should those components be placed, such that if there is a failure from one of the manufacturers, the impact of the operation on the network is minimized. And for that, we propose a metric that is based not on the minimum cut set I mentioned before, but on the path set, which is the opposite. It's how many components should be operational for the network to be operational, right? And we propose different algorithms and ILPs that were looking into how many successful flows were still in the network despite the failure of different set of manufacturers. And you could see that our Naga and Zora, so Naga was outperforming better, Zora was only taking into account the availability, and it was performing much better than taking into account criticality or centrality metrics like closeness centrality, between centrality, and so on. Okay. Then moving a bit about to security. As you know, and it has been already discussed also in the conference, you have also the threat of quantum computing that may compromise all the security that we had to now. And it has been accepted that, it was mentioned yesterday by Telefonica, that they are going to take into account both the post-quantum cryptography and QKD, so quantum key distribution, in order to offer secure communications. Since PQKD is more on software, it's more on algorithm and so on, the planning problem implies the QKD, which is the one requires hardware, all these expensive QKD devices in order to guarantee this interconnection, right? So I'm going to look into QKD architecture, so rather fast. You will have the communication in the optical domain for data, and what it is important that the path that you use for the key exchange is different from the data. So for the QKD, you need some service application entity that communicates with this key management, which is the one along the path that is going to have a buffer with the keys. And these keys are the one exchanged in the physical QKD network by these expensive QKD devices. So these QKD devices are exchanging keys all the time and storing the keys at the key MES. So whenever you have a connection from Alice to Bob, he will say, I need this key. I want to share my end-to-end key with Bob, and I will request the KME for the first key of this first link, key 1, and then I will do the XOR, for example, and then I will start sending this key slot by slot, so hop by hop, to my destination. What is important here for the planning is, first, the generation of the keys depends very much on the distance between the QKD devices. So the longer the distance, the lower the keys that can be generated. And secondly, usually these KMEs, because they need power, so they are placed in the same locations and the inline amplifiers that are already there for the backbone, optical backbone network. So our planning problem was having a network topology. We have different alternatives of how many QKD devices we could place and how many fibers we were using for the key exchange. And then, according to this distribution for the key generation rate, because it's never fixed, we were then doing an ILP to optimally place the minimum number of QKD devices that guarantee the keys that we needed for those demands. Okay? And this showed a significantly advantage and reduction of the number of QKD devices, 40%, almost 40% savings when you have low encrypted traffic. And of course, the savings become less as the encrypted traffic increases, because at the end, if you have a lot of traffic, you have to put QKD devices everywhere in order to have enough keys. Okay? Now, let's move to the operational network. So once we have this network, where we have a rather mesh network, and I said, I am talking about the backbone network. It can be the way of a backbone, mobile backbone to interconnect the base stations. So you have this topology. How can you offer resilient communication on those topologies? So as you know, you have all these protection schemes, 1+1, 1-to-1, 1-to-n. You also have restoration mechanisms, and at the end of the day, they are just looking at an available path from source to destination. It's very important to define the share risk attributes of all the links and all the nodes you are using in the network. What I mean by risk sharing is that components that are likely to fail at the same time because of a particular failure, for example, 2 fibers in the same duct, they should be in the same share risk. Or 2 nodes that are powered by the same power station, they should be together in the same risk group. Or they are in the same area that is likely to have an earthquake and so on. So you need to have these share risk group attributes in order to guarantee that whenever you have a protection path, you are going to find a fully disjoint path, otherwise they will be likely to fail at the same time. It's very important, the monitoring and the fiber sensing. So this will be introduced in the next keynote, because this monitoring and fiber sensing allows to detect the failures before they occur. Whenever you see a degradation of the signal, you can start allocating your flows in another path, or the content, or the computation, or the data in another data center, and so on, before the failure occurs. And in this way, you will minimize the disruption of your service. Okay, and what it is also important is this multi-domain concept. We are always thinking about our availability, I don't know, 7 nines, yeah, 6 nines. From which point to which point? When we look into a network and we look into how many technologies or how many operators we are going through, usually we have to take into account a multi-domain end-to-end consideration of our availability. Not only availability, but also security, also sovereignty, and so on. So we have to be aware about this multi-domain concept, and it was also presented in a project yesterday. How can be, through different operators, how can this be guaranteed that your path is going to be fully protected? And the operators are not happy to share their topologies. They are not happy to share about all the how its infrastructure it looks like, but you just need to guarantee that the two paths are indeed disjoint. The same happens for an operator that is running different technologies. So we are also looking into a particular scenario that we have 5G, wireless, Li-Fi, and so on. How can we guarantee disjoint paths through different technologies? And last but not least, will introduce you about the QKD. So once we have our QKD network that have these QKD devices and is exchanging all these regularly keys between those nodes, we have then the key generation that is according to the distance, and we also have a set of demands. Those demands are going to consume keys. So we are going to have a loop there, of consuming keys and then generating keys, right? And the idea is to be able to exchange the keys end-to-end such that you are never running out of keys at these intermediate trusted nodes, right? But at the same time, coping with all the encrypted traffic. But what we found out is that if you have a single path, you will have only one set of trusted nodes. Each of these trusted nodes will know which is the end-to-end key. So if one of these trusted nodes gets compromised, your end-to-end key will be public. And this is something that you don't want to. So in order to increase the key security, we propose the secret sharing, or the key secret sharing, that is just to have different disjoint paths where you send shares of your key. This prevents that if you have the bad guy compromising one of your trusted nodes, he will only get one share of the key. And in order to get the full key, you need to get all the shares of your key. So you are forcing the bad guy to get, in this case, n copies of your key in order to get the whole key. So we saw that indeed this solution is increasing your security. And the more paths you have, or the more shares you are using, you are increasing significantly the security. However, and also you will need then more QKD devices because you are consuming much more keys. You are using 3 paths, so this means that you are using 3 times the keys. So what we wanted to say is to say, okay, good, we are increasing the security, but what about the availability? Now, if we are using 3 different paths, we ask for the 3 paths to be working in order to retrieve the end-to-end key. So our availability is, in fact, hard, because we need the 3 paths to work, not only 1. So how can we find this compromise? So we said, OK, let's, for example, consider 3 different paths. So we have different shares going through the different paths. But we need less shares in order to get the end-to-end key. So we had 2 parameters, how many disjoint paths and how many shares do we need to find out the key. So, and with that, we wanted to play with both aspects. And we show here in the graph the compromise of how many paths and which is the key availability. So in general, we do not need all the shares in order to retrieve the key because it's too low availability. We want to find the compromise, so it's better to have, for example, 3 disjoint paths, so t equal to 3, but n equal to 2, that you just need 2 shares of your key. And with that, I will conclude my talk. So mainly, I tried to give you a short overview of the different problems for the physical infrastructure and the operational of networks. So what we need is really a real interoperability from equipment from the different vendors in order to have a more sovereign and more robust network. We also have to consider the multi-domain in order to guarantee end-to-end availability, security, resilience, and so on. We also need high connectivity. And by connectivity, again, I'm going back to the multi-domain. It doesn't have to be always the same technology. It's not that I'm defending optical fiber everywhere, no. But we can have a joint interaction with the satellite and, of course, mobile and any technology. So there has to be high connectivity, take into account all these technologies together. And finally, we need an integration of all these technologies in order to guarantee a robust and sovereign network. So thank you very much.
Thank you, Carmen, for a very interesting and timely, I would say, I dare to say.
I hope so.
No, not timely from this viewpoint, timely from the topic itself. So can you put up the lights? And I think we have time for a few questions. So there are microphones available. Anyone would like to start the first question? I don't see any. Anyone? Yes, there's one there, please, with a microphone.
Thank you very much for a good presentation. Robustness is a built-in functionality. And robustness is part of resiliency, as you know. And resiliency is more than robustness. Resiliency, withstanding, withholding, and also recovery and restoration. And also, the other aspect is for robustness, you can do things based on the known aspect. But for resiliency, there are unknown aspects. For example, new threats, evolving threats. What sort of methods could we bring into the game that we need to reduce the duration of disruption, actually? And that is the important. That is money, actually. And could you elaborate on that, please?
Yeah, it's true. So that's a good question. So when I focus on robustness, I mainly look into the physical layer, so mainly the connectivity of components and so on. Then there is the operational layer. I didn't look into that, so I mainly mentioned the protection schemes, for example, right, or the restorations. This is part of the end-to-end failure management steps, as you say, right? So detection, localization, reaction. So if you have protection, you will have a much faster restoration because then you will have just either you have a 1+1 and you don't have to do anything just to restore the failure. If you have a 1-to-1, you will have some basic protocol in order to swap. So it depends on the strategy you are using. You will reduce the service restoration or the service disruption time. At the end, it's always a matter of your control and management plane, also the use resources. If you have 1+1, you are using twice the resources, so you will only doing for customers which are willing to pay for that. Or if you are in an optical backbone network, definitely are always having 1+1. So depending on how much traffic you have. But if you go to aggregation or to access networks, then it's really very punctual how much resources you are devoting for the customers. Yeah? So if you are in an access network and if the operator comes to you and to say, okay, how much you are willing to have 1 9 more per year, I don't think that none of us will be willing to pay, I don't know, 10 or 20 euros more per month. But the company will do it. And that's why some companies, depending on the business, will have this joint infrastructure in order to minimize the service disruption time. So there are many aspects there that they have to work together, also with the fiber sensing that we are going to listen in a minute, or also the early detection of the failures will help to reduce this time, because if you prevent, you are starting to detect that there is something wrong, I am losing power, the quality of the signal is dropping, I can switch already my connection somewhere else and reduce the service interruption time. So, yeah, thank you.
Any other question? One more? Okay, please, the microphone here. It's coming that way.
Thank you. Thank you, Professor Carmen. I enjoyed the talk very much.
Thank you.
And when you're doing the presentation, I can't help but wondering, if we can associate something about a value, typically like a monetary value associated with your work, we can probably make the message more convincing. For example, in your slide number 37, the resilient communications, you did lay out those foundations, those work that we need to do, right? And then so that we can protect our network much better. And those are very valuable suggestions. However, if I want to present it to some people who are willing to invest in this part, right, then if you associate this like a money value or something associated with that, it's probably more convincing, mainly because, for example, you measure the network downtime, but you know the damage that during the business hour, well, people will lost more value than like in the non-congested hours, right? So I'm wondering, how do you think about maybe if we can add another factor, another tangent, then probably can make our message more convincing. Thank you.
Thank you. I mean, it always depends very much on the network segment you are working on. Because when we look, for example, on the optical backbone, all this traffic is aggregated. So it's not that you have so significant variations of the traffic. Now it's mainly triggered by all these data centers. But the more you go to the access, then the more differences you have on all these traffic profiles, and you can see the usage of your capacity. So yeah, there are definitely more aspects that they have to be taken into account. I also want to mention that it also depends very much on your business model. So who are you, which type of operator you are. If you are a network operator, you may have your own physical infrastructure, or you may lease physical infrastructure. Because now there are so many physical infrastructure, train companies, power companies, they already have their optical cables, or cable labs, right? They are installing cables with 1,000 fibers, and just to lease this capacity. At the end is the business model you have to evaluate. How much do they cost? Is it worth for the capacity that they need? And how much spare capacity do I have of my resilience? So it depends very much on the use case, right?
Yeah, I agree with that, because for example, in the restoration, right, when the damages happens, then if we want to recover, we need to set up priorities. So what the priorities were based on. Okay, thank you.
Thank you. Please share with me a round of applause to Carmen. Thank you very much, Carmen.
Thank you.
Thank you for coming to Malaga. It has been a pleasure. Thank you very much.
Muchas gracias. Thank you, gracias.
So we go to the next keynote, which is a colleague coming from Ireland, Marco Ruffini. So as you know, he's a professor and a fellow at Trinity College Dublin, which actually will be the organizers of next year's edition of EuCNC. So let's say it's kind of an appetizer for Dublin.
Thank you.
Marco, the floor is yours.
Thank you, Luis. Okay, thanks everyone for coming here today. So today I'm going to talk about sensing. So when network sense, and so basically what I want to tell you is going through how does sensing work. I'm going to divide my presentation in 3 parts. What are the applications that are used today, and how do we scale? So how do you go from today's sensing application into a network that can sense everywhere? Now, we have a world of fiber. Now, every message, every call, every video you have downloaded, every online calls that you have made, they all have gone through one of these fibers here. Okay? Sorry. Yeah. Now, in fact, if you look at them, they look like veins, right? These are the veins, and they carry the blood, which is the data for our digital society. Now, there's a lot of them because we basically have about 5 billion kilometers of fiber already deployed worldwide. And part of it is only 1.5 million kilometers is undersea fiber, although that small percentage still brings 99% of intercontinental traffic. Now, it makes sense because continents are mostly divided by water, so if you want to go to another continent, you need to use that type of fiber. Now, one question is, that fiber is so important, does it ever get damaged? And I think here, thanks for Carmen, I can skip a little bit of the discussion. So the truth that, it absolutely does, and that's actually damaged a lot. Now, it's hard to find real figures or comprehensive figures, but normally, in a country, could probably see about 1,000 or even more fiber cuts in a year, right? And those all have to be repaired. Now, thanks for the redundancy, a lot of the times you don't lose the connectivity, right, all the time, because there are other fibers that can be used at the main time. But it is still indeed a problem. It has to be fixed. And typically, these are cut by digging, right? If there's any digging, any construction, by far, that's the way they get cut. Now, if you go to the seaside, then there's more reliable numbers, about 150 to 200 globally. Again, it costs a lot more to fix them, and some of them can take a lot of time. Like, some of these took years to fix. And again, it really depends where it is broken, how reachable it is. Some of those are under the ice, so you can't reach it very often. Now, if you wonder why do you get fiber cut in the sea, by far it's by accident. So mostly it's fishing trawlers or vessel anchoring, although more recently we've known that not all of them are by accident. Some of them are being malicious. Okay, now is there anything you can do to that? I know once the fiber breaks, as Carmen just taught us, you will fix it, right? Or else you can bypass. But is there anything that you can do to avoid getting broken in the first place, right? I mean, it would be nice if the fiber could tell you, well, I think someone is trying to dig me out, right? Help. And that's the idea. So the idea is that could the fiber in any way tell you something is approaching that? And again, before you break a fiber with a digger, it's not instant. The digger has to start digging a little bit before it gets to the fiber. So there's a lot of movement and vibration. Could you soon sense that? And the same thing is, of course, for the seaside. Now, spoiler alert, you can absolutely do it. People have been doing this type of things for over 20 years. And the principle is quite simple. So any strain or temperature or pressure in the fiber is going to somehow modify the fiber a little bit. So what you do, you send your optical pulses through the fiber. And if the fiber is modified locally, then the signal is going to get modified locally. And just by detecting that, measuring it, you know it. And again, this has been used for many years to sense temperature. It's been used on bridges to sense, is the bridge stable or is it oscillating too much? You can look whether someone is crossing your fence. You can see if it's a dog, an animal, or is a person, which is malicious. Or, as I spent some more time, you can also detect vessels or very large mammals on the sea. Now, I'm going to introduce very briefly a few techniques, just to give you an idea. So I'm going to make a distinction based on propagation and feature sensed. So propagation, basically, you can either sense by sending a signal and receiving it in the same fiber that you send. So this is due to reflection. And the other is by forward propagation. It's like you transmit data from one part to the other. You check the signal at the other side if there is anything that suggests there's been a sensing event. Now, what do you sense? Well, light is a wave, right? So if it's a wave, you sense the property of the wave, which is phase and wavelength, amplitude, and polarization. And I'm only going to just focus on the first two, just to be short. OK, fiber sensing mechanism. So backscattering basically means I send a signal, and I wait to see what's coming back to me. Okay, it's a small, tiny fraction comes back to me, but that's enough to be detected. You can see, how do you do it? Well, you send a pulse, and nothing happens in the first case. So you record what's happening. On the second pulse, if something happens, you can see there is something there, and you just measure the difference across all the pulses. So pulses of light is like sampling your event. As you send pulses, you get different parts, and you look at the difference between them. What's the advantage of this type of sensing? Well, it gives you accurate localization because it's like a radar. You send a signal, you wait for the feedback, you calculate the time, and you know where it happened. And also, it's nice because the source and the receiver are at the same location, so you only install in one place. Now, of course, because the fiber is very efficient for transmission, it was built on that purpose, it doesn't reflect back a lot of light, so you need a very sensitive receiver. Other things, doesn't allow with optical amplifier because they tend to block the signal back. And how fast you can sample in terms of the length of the fiber, because you can only send a new pulse once all the backscatter from the previous one has finished. So then, or else you could do based on forward propagation. So you send your signal, and then, again, something will modify your signal locally, some event in there. And when that happens, at the receiver, at some point, you'll notice something different. The advantage is that, first of all, you can use any data channel as a source, because it's from one side to the other. You just measure any data channel, the polarization, and you can use it. You can sample much higher because it's just signal comes to the receiver. You can sample as fast as your technology allows. The problem are that it doesn't tell you where it happened. Okay, it's not like a radar that gives the feedback. And the second point is that there's noise accumulation that goes across the whole link. Now, in terms of what you can sense, again, I only talk about phase and polarization. So phase, it basically means that you send a pulse, you get a certain phase at a certain point, and the next pulse, if something has happened, because the fiber is modified locally, the phase is going to be changed. So you measure the change in phase. The good thing is that you're working at micron wavelengths, and you measure a fraction of that, so you can really get very sensitive. You can measure strains of tens of picometers accuracy. The bad part is that, of course, you need a more complex receiver, because you're measuring phase. It's called a coherent receiver. And the other issue is that phase has a 2 pi. Right? When you measure the phase has 2 pi. So if your strain is very strong and you go multiple pi's, you really lose that information. So you don't know how much strain is going to happen. Polarization, on the other hand, basically means that light is an electromagnetic field, so it has a polarization, so direction. And if the fiber is strained or something, that polarization changes, okay, for a moment. And then again, you can record that. The good thing is that you have much lower cost receiver. In fact, in coherent receiver, now they are trying to build this directly into the data receiver, so you don't have to buy anything else. But it's less sensitive than phase. Okay, that's just very brief things on, gives an information how do you do the sensing. Now, what are the applications? Now, the nice thing is that with one sensing system, you can actually do a lot of different applications. So pretty much, there is a little bit more, but pretty much what I described is how you do sensing. But you can apply that to a very large number of applications. And I'm going to just here briefly divide between point sensing, which means the fiber is a specialized fiber that just measures something at a specific location, or distributed sensing, which means you actually use the entire telecom fiber as a sensor. So you could have 100 kilometers of fiber used as a sensor. I'm going to be very quick, just some example, but I think they're interesting way of doing it, right? Very clever. So you can have a gauge level. So the way this, for example, works is that you send light here, and because of the glass-to-water interface, the light actually gets into the water, doesn't get reflected. But the moment the liquid goes out, now you have a different interface here, and your light gets reflected, and you get light at the detector. Very simple. Now, why would you go to that trouble? Because there's no electrical parts, it's chemically inert, so this is things that you use in very specific conditions. Or else you can make an optical gyroscope, right? There's a specific effect. You have a fiber, you send the signal in 2 directions, and as the object moves, one path becomes shorter than the other for the light, and you measure the difference. Some other interesting things are in biology, right? You can build a specialized fiber where this refractive index depends on a chemical reaction, and this shows a very nice example. Like if I want to look at how many targets a biomolecule are bounding here, if I build this in a specialized way again, you can see that, for example, in this case, the wavelength that's reflected depending on how much of this reaction has actually happened. So if nothing has happened, I get a certain wavelength, and as this happen more and more, this property change of the reflecting material, and then you get a different wavelength, and you can measure it. Again, it's nice because it's real time. You can operate it remotely because you can have a fiber that maybe goes 10 kilometers before reaching this place, and it's non-invasive. Last of the localized, this is a very well-known effect or type of device. It's called fiber Bragg grating. This device basically is a kind of, you etch into the fiber a number of these things, and each of these basically gives you a reflection. The interesting thing is that only because they reflect at different phases, it's only when the light matches the periodicity of this grating that you get the wavelength reflected. So this is like a filter reflects only one wavelength. Now the interesting thing is, if I strain it, that grating periodicity changes, right? So if that's strained, the reflected wavelength is going to be changing, and the change in the wavelength shift depends on how much I'm straining. That's a very clever device. This is very precise. Same thing with temperature. Temperature is, means you change the electrical length of the fiber, of that piece, so that works that way. Now, again, it's no electrical parts, it's high precision, you can read it remotely. You can put this device in a place, but you can read it from 10 kilometers away by having a fiber get in there. Now, let's go into the more interesting part, maybe, for networks, which is distributed sensing. So distributed sensing is really when you have a device, it's attached to a fiber, and you sense all the way to the end of the fiber. You know, they could be 50 kilometers, 100 kilometers, and so on. What are the applications? What we're seeing today, traffic is one of the applications. Again, you can have a fiber that goes 100 kilometers. This works well because normally fibers are laid on the side of the road because it's easy to access them and so on. And you can see that, you know, as they go along, you can get a signal and you can see what it is. This is a publication from a very well-known professor, Biondi. And for example, you could see a few interesting things that, you know, whether it's a bus, a truck, or a car, it leaves a different signature. So you can actually detect what's going on. And also, by looking at the slope, you really get the speed, because you see how fast the car moves, and that's reflected in there. Other application that's been used for a long time is earthquake sensing. So why would you do that instead of using localized seismometers? Because localized seismometer, you know, each seismometer is one signal. And you have to put them in different places, you have to power them electrically, and you have to connect them to give you feedback, right, from the network. In some cases, you know, if you're very remote, there's no connectivity, you just leave them there for a month, and then you read them back. With fiber, again, you have a fiber, you can organize the fiber so that you have a reading every 10 meters, and every 10 meters giving you a reading of pressure change or vibration. And then you can, I mean, if you are a geophysicist, then this is very interesting because now you can get a lot more information on what's happening. This publication specifically was very interesting because in this case, by looking at the different in reflections of some of the waves, they basically realized that there might be something different here, and they found out that there was a fault zone somewhere in Iceland. Okay, that's a very interesting application. Now, we go more into the marine awareness, so really into our domain. This is work that we've done within my group, at Trinity College Dublin. This is about trying to solve an issue of detecting dark vessels. So what's a dark vessel? So a normal vessel is a vessel that goes by, you know, doing its own business, but any vessel above 300 tons is obliged to send a beacon that tells their ID, their position, where they're going, their flag, a lot of other things, and their speed. Now, if a vessel above 300 tons does not send that message, it becomes illegal. It's a dark vessel. Now, that beacon is picked up by satellites, is picked up by ground stations, is picked up by other vessels, especially, you know, this is very important for collision avoidance. You know, if you're in the ocean, nighttime, you can't see anything, right? So the only way that, you know, that you're not colliding with someone else is the other broadcast a signal saying their position. Right? Now, the interesting thing with fiber is that, you know, you don't really care what the device is telling you because the fiber is on the seabed, and the fiber vibrates whether or not that vessel is dark, right? It's a physical effect. If the vessel moves, create noise, then you can detect it. And here you just see an example of, this is real AIS, this is called AIS, this beacon, recorded. And you can see that, you know, if they are beaconing, then you can see them going there. And this is a cable, and we'll see in a second what we did with that. So what do you do then to detect the vessel? You know, you want to build a machine learning model that can detect them. So the first thing, you got to collect data. The way you collect data is, again, you just look at this vessel randomly going by their business, and as they get close to the cable, you detect them on the cable. Now, something that's very interesting, again, the way we know these are this vessel is because they are beaconing their AIS. So we use the AIS as a label for the data. And this is the spectral analysis of the signal we get on the fiber. Now, something that immediately you see very interesting is that two things. First of all, vessels got lines, okay, very clear lines of vibrations. And that's very interesting. The second thing, the different vessels are actually show different lines. And that tells you that, you know, maybe if you get enough data, you might be able to actually start classifying, not just there is a vessel, you know, what is it specifically? So with that, for example, in this case, we built a machine learning system based on transformers that detect and classify the vessel. And you know, over time, you get a little bit better. At this stage, we're able to have a detection accuracy of 98%. And then we can even tell you what the tonnage of that vessel is by just looking at the signature. A bit less precise. Now, interesting now, so we use this data to build your machine learning model. And again, you need the label, so you only train on vessels that are legitimate. But then once you have the model, then you go back and you run the data again and say, is there any vessel that I can see the signature, but I cannot find the label? So dark vessel. And we found 41 in 35 days, and the Irish is pretty small. Right? Now, spoiler alert, turns out some of those are fishing vessels that, in order not to reveal their position to other competitors, they kind of turn it down a little bit. But still. And how do we know it's a dark vessel? Because we can't see it. Well, because our system went crazy and says, oh, I'm pretty sure there is a dark vessel there. And then you look at the signature, and again, that looks like a vessel. It's all lines. Now, other thing, interesting thing, because this is a kind of dual-purpose type of project, is with the Irish Defence Forces. Something we have to do is, all these vessels here, they just go by their own business. So you don't tell them what to do. They just go and you measure them. But in this case, we got a large Navy vessel for the whole day, and we told them, I want you to do this maneuver. I want to see if I can check this or this. It's interesting to see what you actually can see. An example is when basically we told them, turn off your transceiver, do whatever you want, don't tell us, see if we can guess it. And that's what we got. So over time, you see that you get the signal, then it goes away, you get the signal, goes away. Now, the signal comes back, so the only way you can do that if you cross the fiber at different distances, so you zigzag around them. Other thing is that, could you detect an anchor? Because, again, if you're malicious, or even if you're not malicious, anchor is one of the most common ways of breaking that fiber. Can you do it? And again, the model sees very clearly and that's actually totally doable. Another use case came from the Defense Department itself. It's like, OK, I have a big vessel, which is legitimate. OK, send your signal. Now I have another small vessel, which is not legitimate, but is trying to hide its physical signature behind the big vessel. Can you get it? And again, if you look at the analysis, yeah, the model wasn't really telling you there too. But the moment you do the frequency analysis, you can see that very different signatures. So definitely, this is the small vessel following the big vessel. And the very last thing, some of these military vessels have a silent stealth engine, which it doesn't go on diesel. It goes on electric power. So a lot slower, but a lot more silent. And they said, OK, let's see if you can get this one. So they turn it on, and you can see it's very, very hard to see anything. But very little energy, but very specific frequency lines. Again, that's another signature that you could say, you're trying to hide yourself. And once you have that, then you can build a system like this. And basically, it's a system we have at the moment that basically identifies dark vessels. Right? So they come up. Now, this is run faster, a little bit faster than real time, just not to stay here for 2 hours. But you can see that now there is a fiber somewhere under there, and as the vessels without a beacon come up, you tell them, here's there, go check it. OK, what's next on this part? Well, as you see, there's a lot of lines. I mean, those lines are physical features. They are produced by some kind of vibration. So the next question is, can I build a model of that vessel just by looking at the lines? Now, it's not straightforward because this will change with, there are multiple resonant frequencies. This will change also with speed. But the idea is that if you process them together, maybe you're able to tell a lot of information. So basically, you build a model of what you think that vessel is by just looking at the resonant frequencies. And that's, work in progress. Now, this, again, is very important this is kind of the awareness side of the talk. Another work, and this is the last part, I'm going to talk about our own work. But another work we did is that you're interested now in here we use what we call the DAS, distributed acoustic sensing. So you send the pulse and you see what's back on the phase. But again, as I said, you can also measure polarization. So you send a signal, you detect it at the other side, and you just look what's changed in the polarization. Now, interesting, because polarization is noise dependent, it's important that you do those tests in a network that can pick up noise. Otherwise, in the lab, you always get 100% accuracy. So from our lab, we injected the signal into, this is a commercial network from EuCNC, which is the national operator. Actually, now it's called the Sierra. Every country has a national research network. But they allowed us to inject our own signals into their commercial network through a certain spectrum. And then you go back, and then you apply some disturbances. And typically, why would someone do that to your fiber? Well, because, for example, if I bend the fiber a good bit, the fiber starts leaking signal, and I can actually take that signal out and read it. So I can eavesdrop a fiber by bending it. That's an example. Or else, digging typically is recognized to be an 80 Hz signal. So if you can see a very strong 80 Hz signal, you can basically say, I think there is a digger somewhere. And again, you build your machine learning, and you can see that even with polarization, even across a noisy situation, you can actually get this pretty good. So the confusion matrix tell you how good you are at predicting what's happening. Okay? So if you're in the diagonal, it means you got it right. So there's nothing happening, and you detect that there is nothing happening. Or else someone is doing a eavesdropping, and you detect it, and so on. And you can see that this actually works. It works pretty well. Okay, so now let's go to the more networking part of that. Okay, because these are all. I mean, I'll show you what it is, but they're all individual applications. Even in the network, it's still one signal going there, and you're trying to see what's happening in there. Now, this gets very interesting then once you try to go into a network, because your network is going to scale it up. Okay. So the idea or the vision is that you got your network, which is a data network, but in the same time, you start putting sensing signals, and suddenly, all this huge amount of information comes up from the network. You can look at traffic flows, as I show. You can look at diggers, if it's striking the cable. You can look at burst water mains, and this is people that have actually detected that. You can see wind or ice. You can look at drones passing by, because drones are noisy. And the idea is that if you can hear something, the fiber can hear it. So that's the idea. And the water, as you saw. What's the advantage? Well, some of the sensing devices are expensive, but in this case, you can share them, because you don't have to sense the same thing all the time. You can multiplex. And ubiquitous. I mean, the good thing of fiber is that it's all connected. Okay? From here, I can go anywhere in the world. Right? So even from this location, once I have a good connectivity, I can sense, in principle, everywhere. Right? It's not that simple, because you have rich limitations. However, there is a lot of open issues, and we're just going to discuss a number of these open issues that people are trying to solve in order to really scale this up to the network level. But in general, all these issues about, if I have fibers here, I want to send somewhere in there, how do I get there? What's the best way of getting there? Considering that my fiber network is a data network, so I cannot just use it for sensing. It's an integrated sensing and communication, but on the optical side. Now, what are the issues? Well, first of all, if I have sensing and data, my question is that data is still the principal application of that fiber. So if I send a sensing signal, it should not affect the data. Does it affect the data? Well, it happens that fibers got no linearity. Well, this is an example of no linearity. So this is a signal which is doing nothing, and this is your disturbing signal. And as you propagate, because they propagate at the same speed, this starts etching into this one, and at the end, you absorb the energy, right? And this creates bit errors. Okay, now this is some of the work that's gone by Cable Labs, and really show that if you put the black one is the curve is when you have no sensing. Sorry, yeah, we have just transmission with no sensing. Red one is sensing in a little bit of power, but as you increase the sensing, the power sensing, then your bit error rate goes up. So you don't want that to happen. So in principle, you have to use less power, but that means you have a lower reach of your sensing. Now, also, what they notice is that if your sensing data goes in the opposite direction of your data, this doesn't happen, right? Why? Because now, if the data goes this way, a speed of light, and this goes this way, a speed of light, they really cross each other for a tiny amount of time. So all the linearity averages out. So there's one issue, but there are some solves. What's the other issue? That people don't really know where the fiber is. I mean, you might have some idea of where your fiber is, but if you're looking at one event, which is the fiber that goes closest to that event is not always well known, right? And the other thing is that even if a fiber is closer than another one, it really depends how is the fiber coupled to the ground, because the ground vibrates. Now, if your fiber is kind of loose, in a way that the vibrations are not transmitted, then you might get a much lower signal from a closer fiber than from one that's further away. And this is, you don't know this, right? No one is going to tell you how well is coupled the fiber. So these is all things that you have to learn, right? And that's where the AI plays a big role. You have to start getting data, looking at the event, how is it affected, and then you start building a database of this information. I'm doing well, I hope. Now, this is another application, right? And this application about, I'm sensing, is one sensor enough? Do I need more information than one sensor? Now, this is a very trivial example, but I think it gives the idea. So this is overhead cable. There's lots of them. So it's summertime, the cable stretches because there's heat, and it stretches during the day, and then it doesn't stretch anymore. But the fiber will tell you, this is stretching. And the operator thought, okay, should I be worried about that or not? Right. Now, if it's summertime, you don't get worried because that's things that happen, right? And normally it's okay. You can do it by design. However, the same thing can happen because of ice load. Now, ice load is a really big problem for cables. In fact, now I've seen there are drones that pass around the cable, trying to hit the cable so that the ice falls off. Right? Now, if you see that, that's a problem. Now, how do you distinguish that? Simple, right? If it's hot, temperature, right? If it's hot, you think, no worry. If it's cold, you think, I'm worried, right? And that's an example. It's very trivial, but where you start putting more information, right? So one information might not be enough. Very more important, even more interesting one, this is Stampenet. It's an operator from Norway, you can see there, and they use both distributed acoustic sensing and state of polarization sensing. So measure both things. Why do they measure both things? There's a very good reason why, right? So here you can see, so basically the main worry is fishing trawlers. They go all the time above the fiber, even if they're not supposed to. Now, what's the problem? So here the DAS is very sensitive. So the DAS tells you that, oh, there is a vessel approaching my fiber, okay? And these are two different times, okay? These happen 2 different times. You can see both cases the fiber approaches. However, something here happens and the DAS here saturates. You remember the 2 pi phase that I mentioned, right? But then it's like, okay, did I hit the cable? But did I actually hit the cable? Or is it just it was close enough? And this, because the DAS is sensitive, it detects that's close enough. But once it goes above a certain level, it saturates, and you don't know. That's where it comes polarization. So they were able to say, well, actually, you know what happened? That in this case, the cable was not hit. It was close to be hit, but it wasn't, because polarization didn't really move much. But here, this is very clear. There was a hit, direct hit on the cable. So again, the DAS will tell you something is approaching, but once it hit the cable, or almost hit the cable, saturates anyway, so it won't tell you. This is another important part of having data fusion. Okay, so how do we solve all these issues? I mean, these are just appearing now. We're trying to solve them now. And this is an icon, is a European project, which is led by Alexandra, a colleague from Trinity College. And it's really about, I'll discuss a little bit more later, but how do we integrate sensing and communication? As well, how do you build an intent-based control plane? Because, sensing is really an application. Data, you send data because you need data, but sensing is an application of this. So you want to automate that. The only thing you want to say is that there's something happening on there, I want to check it. That's what you should be doing. And then through the learning that I showed before, the architecture should be able to basically try to sort out what's the best signal to send there to measure it. Yeah. And this specifically, Altran is looking at this part of the architecture in the work. And again, what you want to do is that you want to decide the route that you want, the type of sensing probe, is it DAS, is it polarization, and then integrate with the SDN infrastructure, because at the end, you want this control plane to decide whether you turn on the signal, sensing signal or not, because you don't want to disturb the other data. Okay. Now, this kind of ends up the main thing that I want to say. So I'm going to conclusion, but don't worry, it's not the last slide. Keep that for a little bit more. So what are the conclusions? Well, I think, first of all, what you've seen is that the fiber-sensitive technology is developing rapidly. It was there for 20 years, but now, because people see new application to networks, is actually developing a lot faster than before. They are trying to make those much cheaper. A lot of things happening. The other thing is that there is a fast-growing range of applications. Okay? And again, I was saying, some of these are just for cable protection. The sensing itself can protect your cables, but also some are environmental. You might want to measure the temperature of the seabed and check how that changes in different places. You can sense the current because, when the tides goes in, water moves one way, the tide goes out, water moves the other way. You can check that, is it all okay, and so on. The other thing is that coexistence with the telecoms is really important, okay? It's not just you reuse, one piece of the telecom. It's really, you become ubiquitous with sensing, because data networks are ubiquitous, sensing network can become ubiquitous. And the other thing we've learned is there's a lot of work to be done there with AI, Because again, people don't know where the fiber is, right? And there's a lot of discovery to be done within the network, and AI is very good at that. However, that's where I said I'm not finished yet. So there are a few issues that have to be solved. No, one is scalability. So a device like a DAS, it produces 1 terabyte of data per day, right? If you think about a 100-kilometer link. I imagine, of course, you're not going to do that, but imagine, you just want to apply to 20% of the fiber worldwide, which is 1 billion kilometers. So that every day that generates 1 million times the data stored in the Congress library. In one day, you produce the whole entire internet traffic in a week, or in one day, you consume the entire Netflix catalogs multiplied by 10,000 times, right? Now you have to store, organize, and process it, so data is a big challenge. People know that. They're trying to find ways of coping with that. The other thing is the integration, right? And the integration means, within the sensing layer itself, but also sensing a network. So these devices give you data. That's all they do. You might decide where you want it to be collected, but they give you data. And then you have to decide, what am I going to do with data, right? So you need to correlate the data. You want to build context around what's happening to have more information for other signals, and then you also want intent-based. And then, again, all of this has been integrated, but all of this has to work with the network side. Ideally, you want your network that decides, okay, is it okay to turn on this signal, sensing signal there, without disrupting anything. And this is, of course, a loop, because, again, there's not a lot of data tabulated available for the type of network. A lot of this, you have to discover it. And the last thing, this is very important, the governance problem. I mean, you're collecting so much data. Now, who should access it? Who can interpret it? Who benefits from that sensing data, right? And again, it's an important problem because you've got one technology. I mean, you got one data stream, the same data stream, and now you can do science, you can use it for resilience, you can do security, surveillance, and other use cases. So there's a lot of issues here, and there's not many laws. And in Europe, even in Europe, many countries do their own things. Like, very classical example, I'm still, right, yeah. Very classical example here is that, I've collected submarine data, and I know that the government really doesn't want you to open it up. In some cases, you say, well, maybe I can check one part of the data. Right? I'm sure I'll look at it, and look, there's no submarines, so I can open it. So I open it, but then, who tells me that my algorithm wasn't that good? And someone else has a better algorithm, and now he says, actually, no, I do see a submarine. So he knows at what time the submarines tend to pass around a certain area, and that's something that the government really don't want to let other people know. So there are issues to be solved. There's one project just ended, a project called Submerse. For example, they came up with this idea that you get the data, the pure data, and only people with a certain security clearance can access the entire set of data. But then what you do is that you can downsample the data. Again, it's like frequency sampling. Sorry, it's like time sampling. So if you sample lower, then you lose a lot of the higher frequencies, and you lose a lot of the information. But for example, if I'm a geologist, I'm worried about earthquakes. Earthquakes move very slowly, right? Hertz or sub-hertz. So to me, anything above 5 hertz, don't care, maybe if I'm a geologist. That's good because, again, I cannot detect vessels anymore, but still I can use the data for science. And this is an example of a model, right? But again, every country at the moment, even in Europe, they just apply different type of rules. But this has to be solved. So how do we solve this? Well, I think the European Commission and European projects are very good at that, and they already started doing it. For example, there is ESFRI, the Forest is a new ESFRI, we're involved, and is building a European fiber infrastructure for time synchronization, sensing, and quantum. And that's a really strong initiative. I mentioned EuCNC, led by Alexandra, a colleague in Trinity College. This is about trying to embed sensing into the optical network architectures. There's another project, EuCNC, we're also involved. Coordinator is from Chalmers, Paolo Monti, most of you will know him. And this is about feeding real-world sensing data into AI/ML pipeline for network automation. And then there are more. Submerse I mentioned, which is more from natural science or geologists, looking at turning the submarine cables into continental scales and civic observatory. Project Sensei, looking at more the photonic side, new photonic side for sensing. And other project Static about joint communication and sensing. So, there's a lot of things going on. What's the next step? This is my opinion. The next step is that there are more CSG, XNS called, and I think it's important that we start keeping or putting fiber into the ISAC in the work program. Why? Because this is the vision, right? So if you, as I told you, if you can do so much by just looking at fiber networks, think how much more you could do if you now do data fusion with wireless RF sensing, whether it's a base station or is high altitude platforms or drones, and even free space optic sensing, right? So you measure all of this, you merge this together, and that is real integration of communication and sensing. So that finished the presentation. Just before, I just want to always like to thank the people in the group. This ARIS group is myself and my colleague Miriam leading the group, and then these are all the great researchers that have done all the things that I mentioned about. Thank you very much. I hope you enjoyed the talk. Good time.
Thank you, Marco. So let me tease you a little bit. So optical fiber is watching you, right?
Yes.
Instead of a big
Right
brother
now,
these
right
days.
now.
Okay, please put up the lights and let's see. We have time for a couple of questions. So anyone? Yes, one there, please.
Thank you. Good morning. Very interesting presentation indeed, opening many venues of research and all. Just a question for the suspended cables. You mentioned snow. Have you looked into the effects of fires, not affecting directly the cable, but nearby? Do you have any such measurements? Because this is happening more and more, especially in Southern Europe.
Sorry, the question?
The effect of fires near the cables on the suspended.
Oh, fire. Yeah. Yeah, I mean, fiber, yeah, okay. I mean, that's, yeah. So a very good way of doing that is with temperature sensing, right, for example. Because, again, the same way I told you, it's like having a microphone every 10 meters, so you could do the same with temperature. You can get temperature reading every 10 meters, and that goes on all the time. I mean, people are doing that, for example, even for other reasons, like we have electrical networks, to transmit the cable, mostly our overheads and so on. Now, in a lot of cases, they're already putting fiber on that to also do communication. But that's very interesting because in a lot of time, they don't really know how much load it's on the electricity, right, depending on where things go. Now, with the temperature reading, you can actually get the load, and that's important because if you want to balance, but it's also important to say, this is getting very hot. There's going to be a problem very soon. And I think that's that's an application. But definitely, anything that sends temperature, it's a really good application.
Yes, up there, please. There. No.
Hello? Yeah. There are many fiber-connected drones being used these days in battlefields, and as the drone gets fired out with the optical fiber connection, it eventually hits its target, but the optical fiber remains on the battlefield.
Yep.
Can that be used as a type of sensor to detect for any intruders coming after the drone has been?
Yeah, we thought about that. I think it's a very good use case. The only problem is that no one wants to go in there and do the tests at the moment. It's a dangerous zone to be in.
It's dangerous.
Yeah, but in principle, yes. Again, the usual thing is that you might not know where the fiber is, right? The whole things. But again, with data correlation, by sensing things that you know where they are, you could start building that. That's for sure. Another interesting application of that is that the fiber that we're thinking about now are undersea telecoms fiber already there, and it is very expensive to put new fiber. However, if I want to send something, I could just put a drone with a weight, send it over, 50 kilometers, let the drone out, the fiber drops into the sea. Okay, that's a new fiber used for sensing for zero cost. I think going ahead, there could be a lot of this interesting application, which may be only, that fiber might not last long because someone might pick it up and so on, but it's something that, you could sense for like a week, maybe with zero cost. Those are really interesting applications with drones, absolutely.
Okay, thank you.
Okay, thank you, Marco.
Thank you very much, Luis.
Thank
Thanks
you
for the
very much for
invitation.
such a nice talk.
Thank you.
So both Marco and Carmen are around during the coffee break, so feel free to talk to them if you want. Don't stand up, please, because Pedro has 2 announcements to take. For me, thank you for coming to this session. We'll meet around. Thank you very much.
Thank you, Luis. Okay, just a few things. First one, you have the application come from me. We have a voting system please vote for the best booth in the exposition. We need to have your input as soon as possible to offer the award tonight in the dinner. Second thing, you know we have 2 private networks, and we are collecting data. We try to collect the data set from EuCNC. Today, maybe next year, it depends on the results. So please, go to the registration desk here and in the other part of the hall. This is the 5G by Nokia. The other one is the 5G with Open RAN. I don't say which is the provider, okay? Both are working. Please register because we need to learn also about the problems. We know we have many problems. Most of them are because of the devices, but this is something we need to solve. And the third, we have an outdoor demo also. Fidal outdoor demo with the police is also in the parking, close to the parking. So please, during the coffee break, maybe you have some time to go there also. Okay, that's all, the 3 announcements. Thanks a lot to everybody.